So the last section on nuclear chemistry involves the process of fission and fusion, and they are the opposite of each other. Fusion is the combining of two smaller nuclei to form a heavier, more stable nucleus. And then fission is splitting a heavy nucleus into two nuclei with smaller mass numbers. So here's an example of fusion: a helium and a hydrogen coming together to form a larger helium and more stable helium atom. And then fission is bombarding a large element or atom like uranium with a neutron and actually splitting it into simpler isotopes, simpler atoms. Now, both of these processes involve a small change in mass. So nuclear changes usually occur with a small amount of mass being changed. So even though you account for the mass in the mass number, there's still a very, very, very small amount of mass that is lost that mathematically doesn't appear to us really in the balanced nuclear equations. Now, because of Einstein's famous E equals mc squared, we can actually take that small amount of mass, and because c, which is the speed of light, is a very large number, it's actually 3 times 10 to the 8th meters per second, very, very large. Because it's a very large value, and then you actually square it in E equals mc squared, you get a very, very small amount of mass translating into a huge amount of energy. So fission and fusion can both be used to produce energy. Now, the process of fission actually is bombarding, as you see in the slide, bombarding usually an unstable radioactive isotope with a neutron, and then causing it to form an even more unstable isotope. And in the process, when that unstable isotope then splits into multiple atoms, you get a tremendous burst of energy. Now, in the fission process, you also get some undesirable products left over that can be radioactive, and those substances have to be taken care of. They have to be stored somewhere. So you get huge bursts of energy with this process, but again, you also get some radioactive waste that has to be dealt with. Now, you can create what is called a self-sustaining fission reaction, much like setting up a bunch of dominoes, clicking the first domino, and that domino hits the next and hits the next and hits the next. And then this just produces an incredible amount of energy. And that's basically what's happening in a fission reactor, which is what you find inside any nuclear reactor. So you have a chain reaction occurring in the reactor core, and that reaction generates heat. That heat then converts water to steam, and then the steam then goes into a turbine, which causes electricity to be produced. Now, some issues with a nuclear reactor is that they can overheat, so you can produce so much energy and so much heat that the heat cannot be contained. The second issue with fission reactors is that you also, again, get some radioactive waste being produced. So, you contain the radioactive waste, and you try to control the amount of heat being generated with some cooling. And actually, most nuclear reactors have very large cooling towers that cool down the water that is then sent into a river or a lake or the ocean. But the water's got to be relatively cool when it goes back into the groundwater or into the river, lake, or ocean. Now, fusion, on the other hand, fusion is actually what occurs in the sun, and this is, small, tiny nuclei coming together and forming larger nuclei, and then again, small mass change, you get this tremendous burst of energy. Currently, fusion is kind of a difficult process to do in the laboratory, and for us it takes more energy actually to cause the fusion than we actually get out of it. So the real issue here in the future is going to be, can we use fusion to produce a sizable amount of energy without putting in a ton of energy into it, because fusion has no real waste products, so it's a much cleaner way of producing energy using and harnessing that energy within the nucleus.